All right, everyone, welcome back. So we're going to continue talking about cryptography. Lots of slides to cover. What I'm going to do most likely is I'm going to continue the lecture until the end of this lecture at 6, like 5:50 or something. If by that time you haven't finished all the slides, I'm going to give you like 10-15 minutes break, and then I'm going to continue the recording. Of course, you don't have to stay. Uh, I'll keep the Zoom open in case anyone wants to stay, but I'm gonna finish the slides for the cryptography part, given that didn't have class last week as well. But again, everything will be recorded. You don't have to watch it now. But just FYI for those of you uh, who wants to stay. Okay. All right, so kind of quick recap. So we talked about the basics of uh excuse me, basics of cryptography. We start with encryption. We introduced the notion of perfect secrecy and why it's helpful for us. We showed that the perfect secrecy can be achieved using one-time pad, which is basically just an XOR. But we saw that XORing requires one important aspect, and that is that the size of the key and the size of the message has to be the same size, which was very, very expensive, unfortunately. So we said that, we need to do something about this, and that's where we introduced the notion of semantic security, which essentially said that instead of using the full K, we can use a S. That size of S is much smaller than K. What the trick is, we're going to introduce a new function called G that you send S and you get K. And this K is the same size as the message. We said that this essentially means that uh, the secret information is much less. Of course, that means that we're going to lose some security, but there are proofs shows that the security is small. So essentially, we only leak epsilon amount of information in some sense. We also talked about G and said that G is not just any arbitrary function. It should be a function that can cause K to look random. How does it do that? How do we know that this K is random? It's based on a series of different statistical tests and so on. And we told you that there are various actual examples in the industry if you guys interested to know. So that was kind of like where we were, and that was the stream ciphers. We also introduced the notion of nonce in order to make sure that the encryption is probabilistic, which means that if you encrypt the same thing twice, it will result into two different numbers. Any questions from that lecture, the previous lecture? All right. So from that, we started optimizing this, and we said the last thing we said last time was block streaming is not the most efficient in terms of encrypting large amount of data. What we want to do instead is kind of like something that in one go can take a block and encrypt it all together. And that's where we introduce the notion of block ciphers, and that's what we're going to first focus in this lecture. For block ciphers, the first thing that we introduced, and that was kind of like examples that I gave at the end of previous lecture, was the notion of what we call pseudo-random permutations or PRPs. PRPs is this one-to-one functions that maps a domain to its own. So essentially create a permutation, right? But this permutation is keyed, which means that the function takes two inputs, takes x and takes k. And based on this k, it creates a permutation for x, okay? Mathematically, we usually use this, if you want to use it for encryption, as e, k, and p, which essentially what it does is that it takes a vector of size k, another vector of size n, this is size of your message, this is size of your key, and then create an output, which is in this case a cipher, takes of size n, which is the same size of the input. The big difference here is that K doesn't necessarily need to be the same size of N. This is no longer an XOR. This is just a key in order to create a new permutation, okay? So what is a secure PRP? So generally any PRP could be, any function could create some permutation. What is secure? Secure PRP should be indistinguishable from a random permutations, okay? We're not going to show you the proof, and they're not going to show you the details. But essentially, this should be somehow that if I see a lot of queries from this function and I see different permutation, I should not be able to tell the difference between this results generated by the PRP versus if I just randomly pick a permutation. Okay? I also gave you an example, a very simple example, that if this is my domain and my key is basically a 2-bit data, then based on key, for example, we can create different permutation. The simplest is if it's k is 0, we don't permute anything. If it's k is 1, we shift it by 1. If k is 2, we shift it by 2, and so on and so forth. Simple permutations. In that case, then, if I want to create an encryption, if I take input 1 and key is equal to 2, means that 1 has to be shifted twice. So we're going to get number 3, and that's kind of our encrypted data. So our ciphertext in this case would be 3. And of course, as I said before, this is not a secure permutation because it doesn't look random. Of course, it looks very, very well defined. So you do 1, you get 2, you do 2, you get 3, and so on and so forth. So this is not a random uh, 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 this is not a random permutation. Okay. Okay, so now using this idea that now we know what is PRP, let's see how we can use PRP for encryption. We already kind of said this and explained this through this example, but the idea is very simple. We take a block, we use a secure PRP to create a permutation, and that's essentially uh, is your ciphertext. And you repeat it for the next block and the next block and the next block, and that's it. You have the response that you have. So this is essentially the basic idea of a block cipher. There are a little bit more to it that we need to discuss, including, for example, how do we create that probabilistic approach that we need to have, such as, we don't want to, if for example, the same number is going to the block cipher, we want to receive a different ciphertext for. Uh, So the question is this semantically secure? And yes, as long as there's proper chaining, and we're going to discuss what is this chaining and randomization. What we are trying to achieve with the PRP is essentially this functionality that it should be very easy to compute this, but it should be very hard to find the inverse function of f, right? So without knowing k, it should be very hard to inverse this function, because if someone can kind of like looking at the permutation tell you what is the x or what is the key, then the system is broken, right? So that's what we want to achieve. How do we build this PRPs? There's no theoretical way or method or algorithm for building PRPs. There are some principles, such as, for example, a good PRP should have some form of a non-linearity in it. Otherwise, the attacker can reverse engineer this. But there is no like a known algorithm for creating a PRP. So what it is most of an engineering problem, combination of engineering and some theoretical problems. That many people over many years has spent time on this. So this kind of quest for finding a good block cipher has been something that's been around for a very long time. Uh, uh, Thankfully, there are very powerful examples for block ciphers. The most famous one is the AES, the standard encryption mechanism. Before AES, there was DES and triple DES and some other algorithms, but the one that is commonly used and still used, and this is a gold standard, is AES. So we're going to talk a little bit about AES. We're going to talk about like the basics of AES. So essentially, AES is looks like something like this in terms of functionality. So you have an input X. This is your message. This is your plain text. Usually we translate the message into an array, a 4 by 4 array of bytes, which essentially each byte is kind of showing like this. So we usually transfer an input and show it as a 4 by 4 matrix. Then what happens in AES is that there is this AES function, this E function, and we repeat this E function multiple times. So we typically do it either 10 times or 12 times or 14 times, depending on the level of security that we want to achieve. But essentially in these rounds, that's what we call them, we apply some functionalities. These functionalities are the same, except the first round and last round, there are a few things that are slightly different. But other rounds you do exactly the same thing. So there are 3 steps that you need to follow. Uh, each round has what we call a round key. So essentially similar to kind of the stream cipher idea. You start with some form of a seed, you expand it. For expansion, you can use like similar ideas to a stream cipher, but remember I told you that this is not very fast. So we're gonna later on explain the key expansion algorithms. But usually from this, we're going to get round keys. So if you, for example, have 10 rounds, we're going to have 10 different keys. We're going to apply these different keys to each round. We're going to basically get the output of each round as the input of the next. So we kind of create some form of a chain. And eventually, after the nth round, we're going to get our final response, which is our ciphertext. Okay. So let's see actually what's going on in the steps. So AES steps are kind of like 4 big steps. The first step before doing anything, it's the key expansion, obviously. So this is even happening even before the message is coming. I'm going to talk about key expansion later. Then we have what we call the initial round key, which we call add round key. Add round key is essentially, it's very simple, just XORing the input with the key. Okay, so and adding the round key means that we take this and we XOR it with the input. Okay, so very first time we're gonna do a round key. That's the first thing we're going to do. After that, we're going to go through this rounds, okay? So we're going to have, as I said, either 9, 11, or 13 rounds, and then there's the final rounds, which is added, so we're going to make it at 12, 10, 12, or 14, okay? So what's going on in these rounds? So in these rounds, in this 9, 11, or 13, we're going to exactly do these 4 steps, okay? The first step is what we call a sub-byte. This is also sometimes called S-box. Subbyte is kind of like there is a table. I'm going to show you the table later. So remember I told you that this is like a 4 by 4 matrix, okay? So basically we're gonna kind of like move this bytes around. So for example, we're gonna move this and put it maybe here, and then move this one and put it here, and move this one and put it here, and so on and so forth. So we're gonna move this bytes around, okay? There is a table, there is a known algorithm for it. It's not like, we randomly move things around. There is a table for it for each round. You take the byte and then you substitute it with another one. Okay, this essentially creates this nonlinearity that we want because this is not a mathematical function per se. It's more of moving things around. Okay, once you move the bytes, then there is shifting the rows and shifting the columns. Okay, so shifting the rows is typically you take the last 3 rows and shift them up in a circular fashion. Columns is also the same, but the column wise. So you kind of like move columns and shift them. So it's kind of like, try to shuffle this data. Once you do these 3 things, then you do another adding round. So at the end of this round, you also do the same add round key, which is, as I said before, XORing this output with the key. Okay. So you repeat this 9, 11, or 13 times, exactly the same thing over and over. So you will get an output here, you feed it into the same thing with a different key, and then you repeat this process and you go this. So this will shuffle this data enough. At the final round, the only difference is that we skip the mixed column. part. So we do the S box, we do the shift rows. We no longer need to do the columns. There are explanations for it if you're interested to go too deep into AES of how, why, and how we are doing these things. But generally, as I said, the whole idea of AES is creating enough randomness in the system such that you cannot distinguish this from a random sequence of permutations. And as you can see, we're not introducing any new data, we're just like moving things around. Okay. This is also a nice visualization of how things are going. So this is kind of like, sub by, then you shift the rows, you mix the columns, and then you add the round keys, and then you eventually you're gonna have this inputs. I also have an example for you. This is again generated by ChatGPT, so you can actually see how things are happening. So we have a 128-bit data and 128-bit key. These are randomly generated, so just some random looking numbers. So as I said, this is kind of like simplified version of AES. I'm just showing the first round, one round of these AES, and then the final round. Okay. So as I said, in the first round, what you do is that you add the round key. Okay. So what you need to do is you take, this byte by byte, you XOR them together, and you get the results out of your XOR between the plain text and the key, okay? Then you start those four things that I told you, the sub byte, the shift rows, the mixed columns, and then finally you will do another round key. So essentially the idea is, for example, in this case, we're going to do 10 rounds. As I said, it could be 12 or 14. So the subbyte is essentially, there is a table. You can actually Google this table and see the actual numbers. But essentially, once you look into to this, you will see that, for example, there is a number, the output of that, it needs to be shifted to somewhere else. Let me see if I actually have. Yeah, don't have it here. But yeah, so you move the bytes around, then you shift the rows. So for example, you take this row and you shift it and move it somewhere else. And then you also mix the columns. So like, you have a column like this, then you shift the columns with other columns in your data as well. And then finally you do another round of XORing with taking the inputs and the key, and then you get the output. The final round, as I said, it's include everything except the mixed column, so you get the final results. If you follow that, you will see that, for example, after that 10 rounds of activity, you will get this final result, which is your ciphertext after kind of mixing these things up. And if you're interested, you can definitely do it step by step or yourself. The good thing about AES is that the code is very well known, and there has been tons and tons of examples for it. Is there any questions about AES at this point?
For the S box, is there any logic to like the substitutions that made, or is it kind of just some random set in stone set of substitutions?
It's random set of stones. As I said, typically these things don't have theoretical. There are thinking behind it of like what is the best way to do it. Mostly engineering. The idea of SBox is mainly creating some form of a non-linearity. Uh, but again, like, the rationale behind many of these things of, for example, why do we shift rows and then mix columns, why we are like taking 3 rows and not 4 rows and so on and so forth. These are mainly just to create that amount of randomness that you want to achieve. There are some theoretical explanations for some of these approaches. The others are mostly kind of trial and error, and they figure out that this is the best way to do it. Okay. So let me talk about 3 important things about AES. The first thing is that how do we do the key expansion? The second question is what happens if we want to, encrypt more than one message? And kind of this third question is kind of relevant to the second question is how and where do we add the randomness? Because remember, for example, in this case, if I repeat this process using the same key and same message, I want to achieve a different ciphertext. Because as you can see here, nowhere in this process I'm introducing a nonce or any sort of differences. So if I repeat this process multiple times, I'm going to get the exact same ciphertext. And remember that that wasn't secure because I want to be able to achieve a different ciphertext each time that I encrypt the same message. Otherwise, the adversary will see the pattern and see the repeated, ciphertext and understand something about my activities. So we're going to actually introduce this notion of nonce into this system. So far we haven't explained that. Okay, so let's talk about this. Let's talk about key expansion first. Remember I told you that, yes, we can do the same generative algorithm that we had before, which essentially takes a seed and kind of expand the key. In other words, block ciphers can use the stream ciphers within themselves, but that's kind of defeat the purpose. If you remember, I told you that stream ciphers are generally slow, so you don't want to do that. Instead, what we do is we're using what we call pseudo-random functions or PRFs. PRFs are very, very similar to PRP. The only difference is PRP creating a permutation, which means that it maps X to its own. PRF maps X to another domain, Y. Okay, so essentially what we do is we take an input of one size like Z, and then map it to another size S, okay? So how does this would work? Remember we had S and K, so this is exactly what we want. So we want to apply F of S and gets K, basically, right? So that's kind of like what we do. And the way that we're going to do it is we're going to use this pseudo-random functions, essentially, okay? So we have this K as our input. We're going to generate this different inputs X1, X2, X3, and so on. These are kind of like, our inputs to this seed, and then we're going to generate this K for these different inputs. X could be, for example, starting from 0, it could be 0, 1, 2, 3, and so on and so forth. And this K is essentially our S, okay? So if I want to generate 10 round keys, what I can do is that I have my seed. I generated one time with Fs and 0, another time with Fs and 1, and so on and so forth. I'm going to get 10 round key. I can keep doing this if I want to generate more and more keys, okay? What's the benefit of this? Like, why do we want to use PRFs and not PRGs? It's just mainly just because the PRFs are very, very fast. So we know very fast PRFs that are significantly faster in terms of time, execution time, and so on than PRGs. That's why we rely on PRFs and not PRGs. Okay. So that's the key expansion part. So essentially, key expansion part is you get the actual secret key, you expand it using a PRF. There's actually what we call an AES PRF. AES itself has a pseudo-random function that you can use in order to expand the key. And then once you have those round keys, and then you then apply your AES algorithm there. Okay. So that's kind of the first question. Let's talk about these two other questions. So the question with block cipher is that the whole point of a block cipher is that we want to encrypt large blocks. Okay, so think about blocks as like multiple pixel of an image, right? So each pixel is a number, right? So or each group of pixels could be a number. So you want to encrypt this, right? And then if you encrypt this, you want to get your ciphertext, and hopefully what you want to achieve after encrypting this, obviously, is not this, right? What you want to achieve is something like this, that if you encrypt this entire multiple block system, you want to have what we call diffusion, right? So that, this ciphertext that is created by this block and this block, they should look very, very different. Otherwise, if, this and this looks like similar, then you will see that, the adversary can kind of see the pattern, right? And that's not what you want to achieve. What you want to achieve is some form of very random looking. So what we need to do is that we need to be very, very careful when we are designing our block cipher. If, each input results in the same output, or at least close to a same output, then we're not going to achieve this level of security. So what we do, there are actually multiple ways of doing this. There's no one way of doing this. I'm going to give you two examples. The one that is kind of like easy to understand is what we call counter mode block ciphers. There's also a bunch of other ways of doing this. Okay, so what is a counter mode block cipher? So say, for example, we have a function e n c k and m. Here M is multiple blocks, so M is has R blocks. Okay, each of those blocks are the inputs that we discussed last time. So for example, M of 1 is the X that we said goes into the AES. Okay. Uh, so what we do is, and by the way, if for example we want to have R blocks and for some reason our input are not enough bits, we typically pad the last one with zeros in order to achieve the same size. So here we assume that all of them has the same size. If they don't, so it's not divisible, you can always pad. Okay. So now that I have our different blocks, these are my inputs, for example, 128 bits. Then I want to create our different ciphertexts, right? So the output should be, some form of a for loop that starts from 1 to R. Eventually, we want to achieve a vector of ciphertext from 1 to R, and that would be our ciphertext, right? So how do we achieve this? We achieve this using this trick. We're going to use what we call an initialization vector, or IV. This IV is basically the same as nonce. Since it's kind of like we are looking at the vector, we are using the notation of vector, but it's totally fine if you want to use the same word that we used before, which is nonce. And here's the algorithm that we are using. We initialize ciphertext, the first ciphertext with IV. This means that the adversary will see the IV as well, but that's totally fine. If you remember, I told you that nonce can be publicly shared. But then what we're going to do is that from 1 to R, the way that we're going to create this is we're going to create this partial I, which is essentially the encryption of IV plus I and K. This E function is the AES, for example, that I described you before. E itself, remember, that has multiple rounds, right? But eventually going to create an input, an output. But keep in mind that what we are actually encrypting, we are not encrypting the message at all. What we are encrypting is the IV plus I. I is kind of a counter, and that's why this is what we call a counter mode. Starts from 1, goes all the way to R. K is our secret key, and essentially what we are doing is that our message in this case is IV plus I. For each different PI, this message will change. We're gonna get to our PI, and then we're gonna basically doing similar to what we did with one-time pass. So we're gonna XOR PI with MI, and that would be our ciphertext. Okay. The interesting thing here is essentially for the same message, we're gonna see a different I. As a result, the CI will be different, and that's where we're gonna introduce our ciphertext. Okay, so this will be the algorithm that we're going to use. This is also some graphics for this. So essentially, this is our IV or nonce plus the counter. This is our I. What we do is that we do nonce plus counter. We feed this into our block cipher encryption. This is our AES. We're gonna get this. This is our P. We're gonna get the P. We're gonna XOR the P with the plain text, and that would be our ciphertext. Okay, this would be ciphertext C1 and C2 and C3, and then remember C0 is actually our nonce, so the receiver also will know where the nonce is. Okay, and we're gonna keep doing this for every single plain text. The only difference between this one and this one is that the counter here is 1 and counter here is 0 and so on. So we move forward with this. Decryption is basically the same exact same process. We take the same nonce and counter, we encrypt it using the same key, and we are XORing it with the ciphertext. And if you remember, if you XOR the ciphertext with the key, you're going to get the plain text. We already discussed that in a one-time path. So this way, we're going to get our plain text back. And this part, this nonce is also publicly shared. Why this is secure? Because even if the adversary knows the nonce, they cannot encrypt the message, because in order to encrypt the message, they have to have access to the key. They don't have the access to the key. They cannot take the nonce and predict what is this P. If they can, they broke the basically the encryption system, which is not possible. So that's why the system is secure. Any questions here?
Wait, so if we're never actually decrypting data, could we also just use like a one-way function here instead of a standard like encryption function?
Well, AES is a one-way function. So in other words, there is no kind of known way of going back in AES. As you can see here, uh, so it's not like if I take Y and go back, I'm gonna get X, because most of these things are nonlinear. So you cannot like go back. So that's why this is the trick that we use, that you basically encrypt, encrypt, encrypt. But technically, decryption is this process here, right? So decryption inside has calling the encryption function for AES.
Is
Oh,
the
gotcha. Thank you.
is the encryption function the same thing every time for AES, or is
Yes.
it something that you define?
Yes, exactly the same function that I just described above. So the function is, as I said, publicly known, always does the same thing. There's nothing changed for this. So it always does the sub byte, add the round key, sub bytes. The only thing that changed, obviously, is the keys, right? So the keys changing from one round to another. Any other questions? Okay, some quick notes. As I said, the initialization. So these are terminologies. You will see it definitely different places. Typically, we define IV as the entire thing, which has the counter, which usually starts at 0 and a none. So the entire thing is called IV. I think the notation here is not. This is not the same as what I'm showing you here. Here, IV and nonce is the same thing, but you can actually call the entire thing IV. But unfortunately, you're not going to see a consistent definition at different places. So sometimes everything is called IV, sometimes called nonce plus counter, sometimes IV and nonce use interchangeably, and so on and so forth. But I think you got the idea that it should be some nonce plus something that is keep changing. Okay. Important security aspect of the system is that your nonce should never be used more than once, right? If it does, then your security is not guaranteed. So in other words, the amount of unique times that you can encrypt is the size of your nonce. Typically, we make the nonce big enough such that we never reach into the problem that we no longer can do it. And typically, these things are created what we call session keys. So we create a session with the new keys and the new nonce. We encrypt many, many messages. We close the session. Next time that we create a new session, we create a new pair of keys. And then that's why we can reuse the nonce. We can start the nonce from 0 and so on and so forth. As I said, there are other ways of doing this chaining. So CTR is not the only way. There are other ways such as CBC and all. If you just Google AES, you will see very nice pictures of all these different types of chaining AES. I think that's actually also taken from that Wikipedia page. So you will see the difference between them. You'll see that there are various different ways of, you can, for example, first combine the ciphertext with the key and then do other things. So there are various things you can do. Okay. And lastly, how did we add the randomness? Essentially, the randomness was that nonce that we introduced in our system. Okay. Any final questions about symmetric encryption? Because for now, I want to then switch gears and talk about asymmetric. Okay. So why symmetric versus asymmetric? What is the difference, first of all? Asymmetric is also an encryption mechanism. The difference between symmetric and asymmetric is that in asymmetric encryption, you use different keys for encryption and decryption. Okay. In symmetric, you use the exact same key. So for example, if I look into my AS counter mode, you will see that this key here and this key here, they are the same values. What is the problem with this approach? The problem with this approach is that now the sender and receiver needs to somehow agree on a key, right? So you need to figure out a way, a secure way of transferring this key from the sender to receiver. But that becomes kind of a chicken and egg problem, because if there is a secure way of transmitting the messages, I might as well use that channel for transferring any message. If there doesn't exist any channel, then I cannot even send a key. So now the question becomes, how do I even share a key securely between the sender and receiver? And that's the biggest problem with symmetric encryption. And that goes through the key management and all. Another problem is that now, if, for example, there is a third party that wants to talk to these guys, then this one has to have the key as well. So now the key is kind of like more compromised and more exposed, because now multiple parties needs to achieve the same key. And if they have the same key, they can basically break each other's encryption. So what we want to achieve is kind of like something that's slightly more secure in terms of key expansions and key managements. Then that's the main motivation behind asymmetric. The idea of asymmetric is I will have one key for encryption. I have another key for decryption. Typically, we're going to use a public key, a key that is publicly shared between anyone, as the key that you use for encryption. But then we're going to use our private key, which is kind of equivalent of the secret key in symmetric, in order to decrypt. So the biggest thing in asymmetric is that anybody can encrypt a message and send me a message, but only the person or the entity that has the private key can decrypt the message. The idea here is that encrypting the messages is not something that is we are worried about, right? So even if an adversary can encrypt a message, nothing bad happens, because the message is already in possession of the adversary. They can also encrypt it, that's fine. What we are really, really worried about is that if the adversary gets their hands into an encrypted message, they should not be able to decrypt it, right? That's where we're taking this private key very, very secure, and that's the most important part of our asymmetric. Okay. What is the good thing about this is that now we don't need to agree on on a key. Essentially, all we need to agree is a public key. It's a pair of keys. We can then publicly share this public key with anyone. So it's kind of like, from today, I can announce that whoever wants to send me a message, this is my public key. Encrypt your message using this public key, right? The good thing about this is that when you send the message to me, I will be the only one who can decrypt it, because I'm the one who has access to the private key. And the other students who see this message cannot decrypt this because they don't have access to the private key. So this immediately fixed the problem of keys, because the public key is publicly shared. The secret key stays excuse me, stays secret. It has the same, correctness requirements. Essentially, the decryption of an encryption should result in the same data. Otherwise, there is no point of using this. Remember, we talked also about like homomorphism. This also applies. And it has somewhat similar security guarantees, including semantic security. In fact, asymmetric is slightly more a stronger security opportunity, given that now the adversary can encrypt arbitrary messages. It has to be secure against what we call chosen ciphertext. So remember, in AES it was chosen plaintext, which means that the adversary could see the plaintext. In this attacks, the attacker not only see the plaintext, they also see arbitrary chosen ciphertext. So it has to be secure against that. This is what we call chosen ciphertext attack. And this is kind of like what I just said, that, in symmetric, the adversary does not have access to chosen messages and particular ciphertext. In public key encryption, they do. And by the way, when we say public key cryptography, we mean asymmetric. When we say symmetric key, it means symmetric. All right, so what is exactly the CCA secure then? So this is chosen ciphertext secure. So essentially the idea of chosen ciphertext is that if the attacker has finite pair of M and C, it still should be unable to decrypt a random message. So essentially the same thing that we said about AES. The only difference is now the attacker sees the arbitrary pairs of M and C's and still cannot decrypt the message. Okay. So how do we build a crypto system, a public key crypto systems? This process is a little bit more involved, a little bit more math heavy. Again, similar to encryption, like symmetric key, I'm going to give you some basics and a little bit of math. But if you're interested, you definitely need to spend a little bit more time to figure things out. Okay. So for public key crypto system, we need what we call a trapdoor function. Essentially, what it is that we need a function that is very easy to compute, but it should be very, very hard to invert. Okay. This is what usually we call trapdoor. The reason that it's called trapdoor is that, the forward way is easy. Everyone can compute that using the public key. The backward should be almost impossible to do it, but if I have the secret key, then I have the trapdoor, so I have the backdoor to decrypt this. That's why it's called trapdoor. So here's a little bit more formal definition of a trapdoor function. A trapdoor function, we show it as T. And we're going to talk about these different trapdoor functions. The most famous one, probably, if you have heard about, is RSA trapdoor function. So essentially, this trapdoor function is a function that is defined over X and Y. And it creates three different algorithms or three different functions, okay? G is a function that creates a pair of key, SK and PK. This is your secret key and your public key, okay? So G is responsible for creating that. It's called a probabilistic function because it's basically take a sample a distribution, okay? So if you repeat this G function multiple times, it provides different answer. It doesn't provide the same key over and over. So it's a sampling function. F is a deterministic function. What F does is that it takes public key and X and it creates you Y. So this is essentially similar to our encryption function, right? So it takes the public key and the message, it pumps out the ciphertext. I is also a deterministic function, and what it does is that it takes Y, it takes the secret key, and it generates X for us, okay? And then you can see that, the big difference between, this is very similar to symmetric. The only difference is that you see SK here and PK here versus in our, for example, PRP and PRF, we had the same K over here and over here, right? So that was the big difference here and here. And of course, these, in order to have the correctness, these functions has to be one-to-one. And so in other words, there are permutations, in other words. And as I said, what we want to achieve is a function that if the adversary sees this, they cannot produce this without having the knowledge of SK. So in other words, it should be very hard to kind of generate this F inverse PKX to generate Y. Otherwise, the adversary can basically break this crypto algorithm. In order to generate this, we need to also have the knowledge of SK. If we have the knowledge of SK, then we are good to go, and we can invert this function, and that's the decryption algorithm in this case. All right, so what are the known trapdoor functions and how they're based off? So the two famous one is RSA and Diffie-Hellman. The interesting thing about these functions and their security is that their security is a little bit harder and more theoretical than AES. AES really, as I said before, is not really based on any hard theory. RSA and Diffie-Hellman and all these other trapdoor functions are actually based on some hard problems. For example, RSA famously is based on this factorization problem, which we're going to talk about. Diffie-Hellman is based on discrete logarithm problem, which we also probably some of you know. We're going to actually talk a little bit about this RSA, and you're going to see the difference between, generally what the difference between RSA and AES, and how this factorization problem play into the security of the system. Okay, so let's actually talk about RSA encryption. One thing that you need to know is that you don't use RSA directly to encrypt or decrypt things. RSA is actually used during this process, as I'm going to explain. So just be careful that since we are saying that this is on RSA encryption, doesn't mean that the RSA trapdoor function is the only function that we use. So this is a slightly different. So let me explain that. So we have a receiver Alice that use RSA trapdoor function to generate PK and SA. Pay attention to the fact that the receiver is the one that is generating this keeper. Why? Because the receiver is the one that's going to decrypt this message, and the receiver is the one that knows the secret key. Anyone else, they don't know. Okay. So what happens is afterwards is that Alice publicly shared this PK with anyone, including the sender Bob, but it keeps the SK to themselves, okay? And then Bob is going to take the RSA trapdoor function F. They're going to encrypt the message and send it to Alice. At this point, F is a known function. PK is also a known function. The only thing that is not known is the message that only Bob knows, okay? So I send it to everyone. Anyone who sees this message, they only see the encrypted versions in some sense. The only person that can know what exactly was M is Alice, because Alice takes the S of SK. It computes the inverse RSA trapdoor function that I, and then she will be able to decrypt the message. Okay, so that's kind of like the steps for RSA. We don't use, as I said, RSA exactly like this. We don't use the trapdoor function directly to encrypting and decrypting. I'm going to show you the algorithm for doing a secure RSA encryption in a minute. But just the general idea is like this, okay? So why don't we do this like this way? Why this is not a good idea to directly use RSA trapdoor function? Because in order for this system to be secured, there are three things that we need to be worried about. First of all, the message should be from a uniformly distributed domain. And like, our English language, for example, messages and all, they're not uniformly distributed. So we need to kind of like first kind of encode the message in some other domain and then use the trapdoor function. Otherwise, there is no guarantee that, the adversary will not learn anything about the message. The second thing is that we, again, have the same issue that we had with symmetric, which we want to achieve semantic security, which means that if I encrypt the same message twice, I want to receive two different ciphertexts. Again, here you will see that since F is a deterministic algorithm, if I encrypt yes twice, I'm going to send the same message. So everybody going to see that Bob encrypt the same message twice. That will leak some information about Bob. So somehow we need to bring some nonce or some initialization vector, some randomization in this process such that if Bob encrypt the message twice, it results into different ciphertext. And lastly, we want this process to be very, very efficient. Remember that the whole point of block cipher was we take a big block and then we can encrypt things very fast. Unfortunately, this F and S, they're not very friendly in terms of time consumption and resource usage and so on, as you can see, because these are, functions that takes a lot of resources, lots of computation. So we need to kind of like figure out a solution for this. So what we're going to talk about, and you're going to see this actually in your project, not next time in your project, is a little bit of these details. But in order to solve those three problems, we're going to introduce this thing called hybrid encryption, okay? And then through this hybrid encryption, we're going to basically fix all of these three problems. And this is what is usually used in standard systems. Okay. So the idea of hybrid encryption is this. The hybrid encryption is going to basically do what we call a double encryption. The double encryption is this, that we're going to use first encryption, and this is an asymmetric encryption. This is like using something like RSA. Uh, what we do is that we don't encrypt the message. What we do encrypt is the key. So we take the public key, we take the secret key of an AES key, not RSA key, an AES key. We're going to take that K, we're going to encrypt it using PK, and we're going to get C, okay? What we're going to do next is, since the user can decrypt this, the receiver, Alice in this case, can decrypt this, Alice knows K, okay? What we do next is we're going to use K to encrypt a real message and send C prime. And now since Alice knows K, they're going to use an AES. So this one is an AES and this one is an RSA. So Alice is going to use our AES to decrypt this and get the message. And from this point on, we no longer need to use RSA anymore because now Alice and Bob agreed on a key. So the basic idea of a hybrid method is, remember I told you that sending the key was a challenge for symmetric? We basically solved that problem using this trick, that we use asymmetric to encrypt the key. We decrypt the key once, and now we have agreed on a key. We're going to later on use this key for further future messages. And that's how we're going to have, from this point on, we're going to have a symmetric. Why do you like what do we like about symmetric that we don't like about asymmetric? Is speed. A symmetric encryption, including AES, is significantly orders of magnitude faster than RSA. That's why we don't want to do RSA for long messages. Okay. So that's one thing. The second thing that we do is, as I said, we don't really want to have RSA directly applied to a message that is not uniformly distributed. What we do instead is what we call this key encapsulation mechanism, which is kind of like a combination of this problem and these two other problems. So let me explain how this does work. There are multiple steps. I'm going to first explain what are these steps, and then I'm going to tell you why. Okay. So the first step, if you remember, for any asymmetric, the first thing we need to do is generating the pair keys of secret and public. And as I said, this is done by Alice. This is done by the receiver. And as I said, this is a probabilistic function, which means that if I run G multiple times, I'm going to get different keys. Okay. Then my encryption mechanism looks like this. So I have PK and M. What I'm going to do is this. Remember I told you I don't want to use message directly. I want something that is uniformly distributed. So here's the trick that I'm going to use. I'm going to take a domain X. This domain could be, let's say, any number between 0 to 2 to the power of 127. I'm going to randomly sample a number. So I'm going to basically generate a random number. Now you can see X is actually uniformly distributed, and that's all I want. Then I'm going to apply the trapdoor function on x, and you see that x now has the property that I want. I'm going to get this y from this x. So I basically just create a random number and I encrypt it using f. Another thing that I'm going to do is that in order to generate k, I'm going to take x and I'm going to create a hash of that. Later on, I'm going to describe hash. But for now, just know that hash function is a function that takes an input, an arbitrary size input, and generates a smaller size output. I could just directly use x, but typically we don't do that. We create hash functions such that to reduce the size of x, because the key doesn't need to be as large as the input size. For security reasons, I want x to be large, but I don't need for k to be that large. That's why I hash it. But again, if I didn't do it, k could be also equal to x, okay? So now that I have my k, here's a trick that I'm going to use. Now I'm going to use a symmetric encryption to encrypt M with K, and that would be my ciphertext. Okay, so this is AES basically. Okay, then what I'm going to do is I'm going to output Y and C. Y was the ciphertext generated by the trapdoor function. C is the ciphertext generated by the symmetric function. How does my decryption will look like? As you can see, decryption has the secret key and Y and C as the input. Two things I'm going to do. I'm going to compute the inverse function of S using SK. And remember, that's the only person who can do this is the person who has access to SK. Inverse of SK and F will give me X, because remember that F was a PKX include, created Y. So YSK will give me X. Now that I have X, I'm going to compute the same hash function that I have. This hash function is actually a public knowledge. Anybody can do that, but nobody has access to X. But now the receiver Alice has access to X, so they can compute K. Now that I have K and I have C, so all I need to do is now applying a decryption of a symmetric decryption with K and C, and boom, I'm going to have my message. So that would be the final output. This is what we call a key encapsulation mechanism, because essentially the key itself is also encapsulated in this process. Why do we do this? Because first of all, I don't want to keep repeating RSA for every single message. I want to do it once for the key, and afterwards I want to just use symmetric encryption. Second of all is that it's insecure to directly apply a message to a trapdoor function. Trapdoor function should be only applied to messages that are uniformly distributed from a large domain. That's why I only apply F to an X, which is coming from a large domain that's randomly sampled. Because of these two reasons, I'm going to generate this. Another interesting thing is that this also solves my second problem, which is the randomization. As you can see, each time that I'm encrypting, I'm sampling a new X, and sampling a new X creates a different key for my encryption. As a result, this process, if I repeat it multiple times, will generate different results each time. Okay? And remember, I don't need to do chem all the time. I do chem once, I get K, and since from that moment on, I just use my regular AES using CTR or CBC or any of those things. So my nonce at that point can be initialized, and I can just move on with that. Hopefully that's I think here, yes. Hopefully that makes sense. Any questions at this point?
I have a question. Is there anything specific, like special about what qualifies as a public key or what qualifies as like a private key, or could like either one work in for either like encryption, decryption algorithm?
Yeah, so there is usually the specific generation algorithm that creates PK and SK. This is also called generator function that is also has to have some properties. So it's not like I just randomly pick like 5 as my public key and 12 as my SK, and that will generate the results that I want.
But could like a public key, like say you just like you generate the public key and private key. Could the private key be used as the public key and like vice versa? Does it matter which one um
Oh,
is
which one is public key and which one is
yeah.
private key? Yes, usually it doesn't. Actually, I have an example for an actual RSA trapdoor function. You will see that typically in order to create this, public key is something very simple. Like it's like a small number, like either 3 or 27. Typically, this is kind of like a common number. And then SK will be something that is a little bit more involved, like usually a larger number. Actually, once I give you an example of RSA, it will make more sense of what is the actual number for PK and SK.
Okay, thank you.
Mhm. Uh, Actually, let me do this example, and then we're gonna give you a short break. So this is the actual RSA trapdoor function. So here are the steps. So g of s, as I said, it's a generator function for RSA. Since we are relying on the co-prime numbers, g of s will create p and q, and this is our kind of public and private in some sense. They're not exactly public and private. But these are two prime numbers that are very, very large. So usually we want our numbers to be in order of thousands bits. So these are very, very large prime numbers. So G of S basically picked two very, very large prime numbers as the output of G of the G function, okay? And as I said, this is random. So if you query G multiple times, it gives you different prime numbers. But these prime numbers have to be very large, okay? Once we have this P and Q, then we're gonna multiply them together, and that's gonna give us N, okay? N is very important aspects in RSA trapdoor function. Once we have N, there is an interesting property about N, and that is phi of N is equal to P1 times Q1. What is phi of N? For those of you who know a little bit of math, this is what we call a Euler function. So Euler function is essentially this function that counts how many numbers smaller or equal to n has no common factor with n. In other words, what are the co-primes of n? Okay. And for prime numbers, we know that phi of a prime number is p minus 1. Essentially, any number from 1 to p are co-primes to p because there's no common factor with any number with a prime number. That's the definition of a prime number, right? So phi of a prime number is p minus, phi of, let's say p is p minus 1, okay? So, and then another aspects of this Euler function is that if you have a situation like this that n is a combination of two prime numbers, then phi of n is actually in fact p minus 1 times q minus 1. These are again mathematical definitions for those of you who probably seen this in high school or something like that. Why do we care about this? You're gonna later on see why this is important, but generally we create two prime numbers, multiply them together, that's our n, and there's a big, there's important property or feature of n is that phi of n is equal to p minus 1 q minus 1, okay? All right, so once we have that, then we're gonna do this second thing, and that's creating our E times D, okay? So we want to find two numbers E and D such that E times D is equal to 1 mod phi of n. And remember, phi of n was P minus 1, Q minus 1, okay? So I want to find ED such that if I multiply them together and divide it by phi of n, the remainder is equal to 1, okay? And again, later on, you're going to see how this will play out. Once I have this E and D, and then this is where I said that we usually kind of like, this is where we need to decide on E and D, and this is basically our public and private. Our public key then becomes N and E. Our secret key becomes N and D. Okay, so this is, so essentially secret key and private key in RSA is a pair itself. How do we pick this E and D? We usually make this E some number. As I said, usually like a 3 or 21 or 27, some prime number, and then find like iteratively go through the phi of n times E plus 1, and that will give us D basically. Okay, I'm gonna actually give you an example of real numbers after this. So once I have my E and D, then I have my private key and secret key, sorry, and public key. Okay, N and E is my public key, N and D is my secret key. And here's the big thing about RSA function, that essentially RSA function, as you can see, if I know N, okay, and if I know E, I should not be able to tell D. If I can find D, then basically this algorithm is broken, right? And why we cannot find D? It's because in order to find D, I need to first find P and Q. Okay, if I can't find P and Q, then essentially it's very quickly I can compute phi of n, I know E, and I can find D, right? So that's very simple for an adversary. Why can I do that? Because this hard problem that I said earlier, that it's hard, this is actually proven, that it's hard to factorize a very large number into its prime factors. In other words, if I know n, it's very hard to know what is p and what is q. And this has to be, n has to be very large. If n is a small, this is not a difficult problem. So for example, if I give you 33, you quickly can say 3 and 11. But if I give you like 3 billion something, 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 then you probably, it's not going to be easy to find the prime factors. And in fact, people have shown that this is an NP-hard problem, so that if you can solve the factorization problem, there's other problems that you can solve in the NP domain. Okay, so going back to RSA, essentially what we're going to do is we're going to share this N and E, and we're going to keep this N and D. Okay, so what does the F function look like? Remember, this is a trapdoor forward function. So trapdoor forward function takes pk and x. In RSA, essentially the trapdoor function is this. We're going to compute x to the power of e modulo n. So compute x to the power of e and divide it by n, and then report the remainder. What is the inverse function? The inverse function takes what? So this is equal to y. The inverse function takes y, compute y to the power of d. As you remember, d was our secret key here. So this is E and this is D, and then compute the modulo n, and that would be x. Why that would be x? I actually drive the math for you here. So y to the power of d mod n is actually equal to what? Is equal to x e. So I'm just replacing y with x to the power of e. So what we have is x to the power of ed modulo n. If you remember, I told you that ed is actually equal to 1 mod phi n. So basically, I'm saying that ed is equal to k times phi n plus 1. K is a constant. And then here's where that phi of n plays a role. There's this theorem, which is if the greater common divisor of a and n is equal to 1, then a to the power of phi n is equal to 1. In this case, we will have x phi of n. So what I'm doing here is that I'm breaking this down into xk phi n times x. I'm just moving this x down. Another thing that I'm going to do is that I'm going to just change the position of this. I'm going to have x phi n times k, and then times x. Okay. And then what I'm going to have is I'm going to use this formula and see that in this case I'm showing that x of phi of n in this case is n, right? And and then A is in this case X. And we know that X and N is basically we use this formula to get this 1. So basically this is 1. So what remains is X mod of N. And that's basically what we want to achieve, right? So remember that we want to have decryption of encryption of X basically equal to X. And that's what we are getting here, because X mod N is actually what we want to have. One example, let me give you a number example. Maybe that helps a little bit further. And then I'm going to give you a break. So let's say, for example, this is a small numbers. This is not a secure RSA. But we have p equal to 3, q equal to 11. N is, of course, p times q. So we have n is equal to 33. We compute the phi of n, which is p minus 1 times q minus 1, which is 20. Then we need to find E and D. Remember that E and D has to be E times Z should be equal to 1 mod phi n. In this particular case, phi n is equal to 20. So we need to find D and E such that we get that value. We typically, as I said, we start with some basic number for E. In this case, E is equal to 3. Now that E equal to 3, we put D times 3 should be 1 mod 20. We solve this problem through trial and error. Then we're gonna, for example, get D equal to 7. So this is an iterative equation that you need to solve. If you actually put 7, plug in the number, we'll see that 7 times 3, 21, mod 20, that's 1. That's what we want, okay? So now we have our D is equal to 7, E is equal to 3. Our public key basically becomes 3 and 33. Our private key becomes 7 and 33, okay? So now time for encryption. Encryption basically would be message to the power of E. Let's say, for example, my message is 7, and N, remember, is 33. So essentially, ciphertext becomes 7 to the power of 3 mod 33. You compute it, you find it, you see that the remainder becomes 13. So that's your ciphertext. Basically, if you encrypt 7, you get 13. Okay? How do we decrypt? Decrypt is this number to the power of D this time. And remember, D was 7, C was 13, N was 33. You compute this, you go through this whole process, and you need to compute this first, and then there's a whole bunch of things, tricks that is used. Eventually, you're gonna get 4D mod 33, which is equal to 7. And remember, that was the message that we sent originally. So that's the answer of our RSA key. Yes, so I think that's all we wanted to say for the RSA. Let's have a quick break, and then we're gonna come back and answer any questions. Oh, there's a question. If F is given PK, how does F know E and N? I know we can represent PK as a tuple, but in practicing PK store as just a single string of character, does that string itself encode N and E? Well, this is kind of like definition of the algorithm. Typically, it has to be a tuple. Like, you need to distinguish between N and D. Otherwise, you cannot distinguish between them. As I said, usually public key is smaller number, and then N is a very large number, but it has to be distinguished. They have to be differentiable. Otherwise, you cannot do that. Same thing for F minus, F inverse. Hopefully that answered your question. All right, guys, let's have a break until 5:23, and then we will continue. Let's continue. Okay, there's something on the chat. It might be conflicting different topics, but okay, yeah. So as I said, this kind of this is like becomes implementation dependent. I think for SSH. For SSH, the way that one can encode this could be different, and that's why this is different. so as I said, like, this is kind of like just a textbook example. The way that it's implemented might be slightly different in different cases, including the way that we encode this message. Any other questions for this key encapsulation mechanism, RSA in general, or anything in between that we discussed so far? Okay. So kind of to finalize, key distribution in asymmetric is much easier because then you can just share your public key and then you're good. Speed in symmetric is much more faster because of just generally there are much less computation, and the complexity of computation is much less. As you can see, for example, RSA requires you to compute polynomials and e to the power of various different things, versus AES was just looking at the table and shifting rows and all those things, which are significantly faster than computing, I don't know, like m to the power of a very large number, which is lots of multiplications. And security, as I said, these are achieving similar semantic security in most cases. For asymmetric is slightly more stronger, sort of more strong because of the chosen ciphertext versus chosen plaintext. And as I said, we already discussed this. So the hardness of the RSA trapdoor function is the fact that if I see n, I cannot find x and y such that x and y are prime numbers. If I could do it, then I can basically find p and k. Once I find p and k, since I already have, n and d and e, those numbers, like the public key numbers, then I basically can break the algorithm, right? So I have n and e. I have P and Q, then I can easily find D, and then boom, once I find D, then I can decrypt myself and break the crypto algorithm. And one final thing about RSA is why quantum computers and security are kind of two things that are relevant to each other. This is basically based on just what I said, that I said that factorization is a very hard problem. But interestingly, for quantum computing, factorization is not a hard problem. And that's the big deal about quantum computers and why quantum computers, one of the reasons that quantum computers are very, very important and critical is that there are known algorithms known as Shor algorithm that can basically theoretically break and find prime numbers in minutes. What used to, like, for normal computers, we say that this takes years for P and Q to be found. For Shor algorithms, this is minutes. So now the question is, why are we still using RSA? The reason is that Shor's algorithms require about thousands of qubits. What we do have right now, the ones that are actually working, is an order of like 50 to 100. So we're still an order of magnitude short in terms of a powerful quantum computer that can actually break this. With 50, we cannot like do it in minutes. But in future, like how quick, we don't know. But at some point in future, once we have thousands of qubits, then you no longer can rely on on the RSA algorithm, because this statement is no longer true. Okay. So what are we doing instead? We are actually looking into post-quantum cryptography, and that's actually a very popular topic, especially since 5 to 10 years ago. I would say still lots of people working on it, because National Institute of Technology, NIST, is going through a process that they did similarly for symmetric back in 2000 when they introduced AES. They want to also find a standardized post-quantum crypto algorithm. There are actually two finalists that they're trying to okay, someone answered this question that's going. So there's some things going on in chat. That's good. Maybe you can post these things on Campus Wire as well so that all the people can see it. But I can also take a look at SSH. I'm pretty sure that you should be able to extract N and E. It's just a matter of how they basically encode this message, but you should be able to do that. All right, so yeah, so that's what people are looking at these days. There's actually other techniques for public key cryptography, such as elliptic curve and all, that are less susceptible to post-quantum, but just to quantum attacks. But just keep in mind that RSA particularly is vulnerable to quantum attacks, but none of them are realistic yet because we don't have powerful enough quantum computers. Any questions at this point? Okay, so there are a few other primitives that I want to also talk about. These primitives, well, I'm gonna go faster, so I'm not gonna talk about them as extensively as we discuss encryption, decryption. Generally, as I said, I kind of gave you a disclaimer at the beginning of this lecture and previous lecture. This part is a little bit difficult to digest, so don't feel kind of like lost. If you feel lost, don't be disappointed. Take some time to understand this. For this class particularly, we're not gonna need a very deep understanding of this concept at the mathematical level. You just need to know this. But since I explained them, I'd rather explain them a little bit more detail to give you also a little bit of theoretical background. In reality, though, most people are gonna just have a very abstract understanding of encryption, decryption, MACs, and so on and so forth, without really knowing what's going on underneath. All right, so let's talk about three other things. The first one is what we call message integrity. Message integrity is different than encryption. So the idea of message integrity is that I don't want to hide the message. I want to protect the message from any sort of modification. Okay, so for example, let's say I have the same setup as before, Alice and Bob. Alice wants to send a message to Bob, okay? I don't want to encrypt this message, so I send this message in the clear, I send the plain text. But one thing that I want to guarantee is that when Bob received this message, I want to somehow guarantee that this is the same message that Alice has sent. How do I achieve this? Okay. Achieving this requires what we call message integrity codes or MACs. Okay. And most of you have used and seen MACs many times before. For example, when you're downloading a file, in order to make sure that the file you actually downloaded is the file that was on the website and not some, created or changed by someone else, you usually kind of like create a checksum and check that checksum and so on and so forth. That's the same idea, okay? So how do we create this? Like, what's the underlying idea? The underlying idea of a MAC is once Alice sends a message, she also computes a tag. So she used a generation function or a sign function called G of M. It creates the tag. Then not only send the message, also she sends the tag. On the Bob side, what happens is that Bob first checks the tag. How does she check the tag? She basically has a verification function that takes M and compute the tag and see if the tag that he is computing is the same tag as he is receiving. If these two matches, then means that the message has not been compromised. Of course, this is like a simplistic view of this because now the adversary can change things. So I'm asking you this question. If you are an adversary in this setting, what could you do to break this system? Anyone wants to propose a attack in this case? Yes, Leon, go ahead.
Maybe the adversary could change the tag so that way the message can never be verified, and so it'll never ever be used because they can keep just changing the tag.
Great, that's one attack, and that's kind of a denial of service attack. Now, let's say the attacker do want the message to be read. Can we also do some attacks in that scenario? Anyone? Yeah, go ahead, Tayu.
Isn't the generator function generally like a public thing, like SHA or so the hacker or the attacker just generates any random message, maybe
Mhm.
malicious or whatnot, and sends a
Mhm.
tag, and like there's no way to authenticate Alice from Bob's side, like Bob would just read everything.
Okay. So essentially what the attacker will do is that if this is the original message, the attacker can generate a message M prime. They can also compute their tag T prime, and then not only replace the message, but also replace the tag. So instead of sending M and T, the adversary can send M prime and T prime, right? And then Bob will see the message, it sees the tags, see it matches, great. Then it thinks that this is the correct message, right? So that breaks this assumption easily, right? So how do we fix this? We need a secure MAC, obviously. So what I showed you is a good idea. It's kind of has its potentials, but it's not secure because the adversary can easily substitute both message and tag, and then will achieve. So essentially, really, the security here is not guaranteed because in the past the attacker could just change the message. Now the attacker changed message and tag. So what is a secure MAC in this case? Secure MAC should be a function a functionality that can resist against what we call forgery attacks. Okay, so forgery attacks means that the attacker should not produce any valid M and T. Okay, and this not valid MNT is actually twofold. We are basically wants to be able not to create a valid tag for a given message or a valid message for a given tag. So we want both of these to happen. So if you're given a tag, we should not be able to create a message for it. If you're given a message, we should not be able to create a tag for it. So both of them we want to prevent from happening because the attacker can substitute any of these two and break the assumption about authenticity of the message. Okay, so we want to prevent this forgery attack. We also want to prevent from what we call a replay attack. So another attack that the adversary can do is that instead of changing this, the attacker can, for example, see bunch of M and T's. So for example, you send a message, like maybe you say yes, and it has a tag. Maybe next time you say no and it has another tag. And both of these are valid and legitimate tags generated by Alice. And let's say the adversary cannot generate any other valid pair of tags. What the adversary can do though is I can substitute these two, right? So if Alice, for example, is trying to say yes, I can replace this with this pair. It's also legitimately passed the test by Bob. And this is what we call a replay attack. So essentially, we're just repeating this a message pair that we've seen before. Okay. So how do we fix these two problems? I'm already saying how do we fix the second problem? We need to add some form of what we call session key or nonce. For the first problem, we're gonna use secure max. Okay. For secure max, there are a bunch of different solutions. The very famous, straightforward and popular solution is just using encryption. In other words, using some form of a PRF and a block cipher. What you can do is that essentially the tag could be the encryption of the message or any sort of something similar to encryption. So here's what I'm going to do is that if I have a message, okay, and if I have a key, a secret key, I compute the FK of M. This could be, for example, the AES PRF. That would be the tag. So what I'm going to do is I'm going to send you my M and tag. And we already proved lots of guarantees on security of the ciphertext and message. That directly applies to a tag, so we are good to go, right? And the only thing is that we need to make sure that the size of the message and the size of the tag is big enough such that the adversary cannot just brute force and reverse engineer this, okay? And then, as I said, the security guarantees comes from the security guarantees of a block cipher. Okay? So that's one way of doing doing MAC. For longer messages, this is not the most efficient way because essentially I need to go through the process of encryption. And here I need a slightly weaker capability. I don't want to encrypt the message. I just want to create a tag. So there are various different things that people have used. There is one that is famous called NMAC or nested MAC. The idea of an NMAC is essentially if I have like a bunch of different messages, a long message, what I can do is that I'm going to basically chain this together and create a final tag for this entire message. How do I do that? I'm having a key, let's say my F again here could be a simple AES function. Later on, I'm going to show you that this could be just as simple as a hash function. But for now, let's assume that this is still an AES function. So what we do is that we take the message 0, take the key, we compute the ciphertext here, we feed it to the next message. So basically the output of this becomes the key of this function, the output of this becomes the key of this function. At this point, we're going to have the final tag, okay? So one option and one tempting option is that send this as the tag. And in fact, initially, that's what people have used and suggested. The big problem with sending this directly as a tag is what we call extension attacks. The idea of extension attack is that if I have two messages, what I can do is that if I directly use this, essentially the tag of this would be the input of tag of this. So I can generate a new message that is kind of concatenation of these together and use this as their tags without breaking any breaking any crypto system. So I don't want to do that, right? So for example, if I have an M5, if I know the tag of that, I can basically remove this and then send this. So I can generally generate any arbitrary size of tags or just concatenating things together, okay? So in order to avoid this from happening, we usually use this T to another function and encrypt it with a different key, okay? Such that this tag, then if I change the size, then this tag will be different. So I cannot extend it. This padding here is just to make sure that the size of this F is the size of the input of this function. If, for example, in most cases, this T is the same size as before, I don't need to be worried about this padding. But typically, you do this padding to make sure that this size is the correct size for this function, because this function and this function may or may not be the same. But the biggest thing is that this key and this key are different. So you need to use two different keys. If I use the same key, I'm going to have the same problem. I'm going to have the same extension attack problem. Okay? So I cascade this. That's why it's called nested MAC or cascaded MAC. What it does is basically just keep repeating the same function over and over again with two different keys. Questions?
So for both of these strategies, you'd have to like securely transmit the keys to the receiver for them to verify.
Of course. So this is the same problem that we have with any symmetric encryption mechanism, that you need to have keys agreed between them. We already know the solutions for that, right? We're going to have a KEM. So they're going to agree on keys using KEM, and then afterwards, they're going to have all these things.
Because like this is a lot of work for, I guess, like for setting up a session, you do this like once and then you do symmetric. But this is only for like beginning a message or beginning a session.
Still you use the same key. You don't need, for every single message, you don't need to change the key. You can reuse the keys for every single message. So very similar to the encryption.
Oh, I
You
see.
agree on the keys one time, and then from then on you move on with this. The only difference here is that there are two different keys. So just one, it's not one key, you have to use two different keys.
Okay. Thank you.
All right, so this is with max, I'm gonna come back to this max one more time when I'm describing hash. So let me quickly describe hash and then I'm gonna come back to max because there is one thing called hash max, this combination of two. So hash, most of you have seen before and used it a lot, not necessarily in the security context. So hash functions are just generally these very useful functions that takes an arbitrary size input and create a fixed size output, right? So hash functions usually gets this keys and create this digest or hashes, right? And they map it. And since usually the input domain is much, much larger than the output domain, there is a possibility of what we call a collision, right? So there's could be multiple things map into the same hash. So for example, this one and this one, in this case, both mapped into this hash. But hopefully if your hash is big enough, then this collision is not very common, okay? So this is a regular hash function. The difference between a regular hash function and a secure hash function, which is usually we call it like, secure hash function or secure hash algorithm, is that secure hash algorithms should be what we call collision resistance, okay? So what is the collision resistance? I'm giving you a kind of a more formal definition. So let's say we have a hash function that takes the message and creates the digest. And then, as I said, usually the message size is much larger than output size. First of all, we define a collision as for function h as if there is a pair of m0 and m1 in M domain such that hash of m0 and hash of m1 are similar, are same, while m0 and m1 is not. Okay? So what is a collision resistant hash function? A collision resistant hash function is that for all efficient algorithms A, probability of A output any collision is negligible. In other words, we don't care what is the hash or what is the function. We just say that if the adversary can just give me two messages that has the same hash, then they break this hash function, the secure hash function. So essentially what as a collision resistant or secure hash function is trying to achieve is that it's very, very, very difficult to find any two messages that produce the same hash. Okay. So this is collision resistance. There's also other properties of secure hash functions. Some of them are common in all of the hash functions, some of them are not. Typically, secure hash function has these other features called pre-image resistance and second pre-image resistance. Pre-image resistance basically says that if I know the hash, I cannot find the message. Okay, so knowing the hash, it's very difficult for me to find the message. Actually, you can prove pre-image using this. I'm gonna let you guys to think about it. And then second pre-image is if I know the hash, I cannot find another message that has the same hash. So basically, second pre-image is kind of derivative of pre-image. Pre-image says that if I know the hash, I cannot find the exact message. Second pre-image is that not only you cannot find the exact message, you cannot find any other message that has the same hash. Okay, so that's kind of like the property that we are talking about. Okay. A big thing about hash is hash are not keyed. In other words, anyone, including the adversary, can compute the hash. When we say something is secure hash, we're not talking about not being able to calculate things. We're talking about if I know the hash, I cannot find the message. But if I have the message, I can easily compute the hash because I have the functionality, I have everything. Okay. That's kind of the duality that we're talking about in hash. For max though, that's difference. For max, I cannot compute the max without the key. Okay, so computing the max require the key, and that's why it's not something that anyone can do. And there are different use cases for keys and hash. As I said before, there is a popular use case for hash and max together. Remember I told you that this functions could be AES function and we don't like it because it's not fast. Instead, people have shown that if I replace the AES function with the hash function, I'm going to have what we call an HMAC, which is get the same property of an NMAC, but it's much faster. It's exactly similar scenario than an NMAC. So if you remember, we had in NMAC, we had a K and a message as the input. This is exactly that. So this is your K, this is your message, this is the next K, this is your next message, and so on and so forth. And as you can see, remember I told you that the last round should be a different K. So we generate this different K this way and generate the final tag. So essentially, in order to create this, we're going to create a key. Remember, this is a MAC, so it's a keyed operation. Initially, we're going to start with initialization vector, some random input. And the reason that we want to kind of XOR it with some pad, there are some other reasons for it that you don't want to know. But generally, this is your secret key. You take the secret key, you hash it with the initialization vector, and that's your key one. And to remind you what was key one, this is your key one, okay? Basically, from this point on, I'm replacing this function with the hash function. Initially, at the end, again, I take this, I generate a different key here, and then again I replace this with hash. How do I generate the second key? Excuse me. I generate the second key with again with the K. The reason I said that I have different XOR is to generate two different keys. So there is this iPad and OPAD that's securely generated, and then we hash this again with the initialization vector, and this will give me a different key, and then I use that in order to generate the tag. Someone asked how the hash function take both message and key as the input. So these are two input hash functions, right? You can have one input hash functions, you can have two input hash functions. There are different ways of defining a hash function, right? So you can have both. Think about like a dictionary search of two inputs, right? So based on first name and last name, then you generate an output. This is the same idea. Did that answer the question? Okay, cool. Any questions from the HMAC and NMAC? So essentially here what we're trying to do is computing a MAC. Initially we use AS, now we are using just a hash function.
What data here would you send to the message receiver?
So I'm gonna send my tag and my M, right? So my M is a vector of M0, M1, M2, and any other size. And then there will be a tag with it. That's what we wanted to do initially, right? Remember that Alice wants to send something to Bob, and we wanted to compute the tag, right? So that's exactly what we're sending.
Do we not need any of like the IV or iPad or OPAD numbers?
So these are usually some numbers that are agreed upon. So IV, for example, is a counter that you can at the beginning of the session you can initialize it to some number, and then from then on they both can go in lockstep. But yeah, you can send IV in the clear if you want to.
Okay, thank you.
Mhm.
Or actually, would you need to authenticate IV being sent?
You don't need to authenticate the IV to being sent because, as far as I know, because if the IV is changed, then it's not gonna pass the test anyway. So it's given that the key is not known, even if the adversary changed the IV, they cannot find a different IV and different message and generate the result. But usually, IV is happening before. So remember that we need to agree upon a key, right? So like K1 and K2, whatever number of keys that we need to agree upon, right? So typically at this point, we already send the IV. So Ivy is not part of the message authentication codes because we already had a key distribution or key agreement mechanism prior to this, which includes the Ivy.
Gotcha. Thank you.
Any other questions? Great. So we talked about hash functions. I think we are almost there. So there are two final things I want to talk about. One is authenticated encryption, and then the second one would be digital signatures. Authentication encryption, or AE, is combination of MAC and encryption. Remember I told you in MACs I don't want to encrypt, and in encryption I don't want to MAC. But then there are many scenarios I want both, because remember, if someone encrypt a message, that doesn't mean that the message I'm receiving is the same message that I'm supposed to receive. But again, because again, the adversary can change things, right? So you can substitute, take out one message and send me another message. So with just the fact that I'm encrypting things doesn't mean that I'm receiving the same message. And MAC, as I said, does not protect the confidentiality of data. It means that if someone send me a tag, it just says that this is the message that you were supposed to receive. So of course, the natural question is, can I have both? I want both the confidentiality and the integrity together. And this is the idea of authentication encryption that gives you MAC and cipher, encryption together. There are two options in this case, right? So you can do encryption and then compute the MAC over the ciphertext. You can first compute the MAC, then encrypt the MAC and send that, okay? The important thing here is that this first option is a secure option, the encryption then MAC. The MAC then encrypt is not a secure option because there has been attack that people shown that essentially the adversary can substitute the ciphertext and that will result in a different message. So in order to achieve AE, just make sure that you always encrypt first, then treat your ciphertext as your message, compute the tag for that, and send that. And that will give you the authentication encryption. On the receiver side, you first verify the tag. That means that your ciphertext hasn't been modified. Then you decrypt, you will get your message, and then you're good to go. Okay? So lastly, I want to talk about digital signatures. Digital signatures is the counterpart of Max. So for Max, I told you that there is Alice and there is Bob. Alice has a message and a tag. It sends it to Bob. Bob gets the message, computes the tag, see if it's matched, then he accepts it. I told you in order for this to be secure, this tag computation should be keyed. So we're going to have the same problem that we have with symmetric keys, that if Alice and Bob wants to agree on a message, they need to figure out a key and somehow send that key. Then another problem is that if there is Chad and there is, David and all those other guys, and they all also wants to authenticate this, all of them needs to know the key. And the problem with this approach is now key is kind of compromised. There are many verifiers. So we need to kind of figure out a solution, very scalable solution, such that if Alice wants to send a message, it can send it to many, many people, and all of them can verify this all together. So it's kind of like similar to the idea of public key cryptography, which I just announced my public key, and then anybody can send me a message, right? So in public key encryption, I send my public key. Anyone who wants to send me a message, use my public key and send me a message. Here is the opposite direction, right? So I want to send message to people. I want them to be able to verify. So based on this, the idea of digital signatures is exactly like this. The difference is that for digital signature, the sender used the secret key to sign. Everyone who wants to verify used the public key to verify, okay? So the idea is the opposite of what we did for example, RSA. With RSA, people use public key to send, and then using the secret key to decrypt or receive. Here we are using the secret key to sign. In other words, only Alice can sign things. So its signed signature is unique to Alice. And then reception and verification is done by anyone who has the public key, which basically everyone, they can verify the idea. How does it work? The idea is very simple to kind of the RSA. So the signature process is like this. I have a message. The first thing I'm going to do is that I'm going to hash this message to make it uniformly distributed. Remember that if I want to use RSA algorithms, I want uniformly distributed. So I hash it, I get this partial result. Instead of using FPK, I'm using F inverse SK to sign. Okay, so this would be my signature. For verifier, the verifier sees the message, or receives the message. They also use the exact same hash function. Remember, hash functions are not keyed and are public. So the verifier also compute the hash, gets the hash here. It gets the signature. It computes the FPK, so the forward function. It gets the value of this p basically, because basically remember this, if this was x and this was your y, this is your y, this is your x. So it computes this hash function of the message with this value. If these two matches, it means that this is indeed the correct signature. As you can see, the only person that can create a legitimate signature is the person who has access to SK. Excuse me. But anyone can basically kind of quote unquote decrypt, which is not actually decryption, but somehow like computing the forward function of signature, because everyone has access to the PK. And this hash function, as I said, is just to make sure that this is the domain that is uniformly distributed and has the same size. So this means that now my message could be any arbitrary message. Any questions here? We are almost done. That's why I'm not just ending the class, but feel free to leave if you need to be somewhere. Apologies that we are kind of running over time. Some final points. So what is blockchains? At some point in the class, if you have time, we're going to talk a little bit about blockchains. Blockchains actually based on these primitives that we have learned. So actually, if you read a blockchain paper or just the blockchain concepts, you probably will be able to learn a lot of it. Of course, there are some protocols such as consensus and all that you need to also learn, but the basics of a blockchain is computing a hash and difficulty of finding a collision in a hash and difficulty of verifying a signature or signing something without having the key. So it's all based on these primitives that we discuss. We're going to talk about it later in the course. Second thing is that it's also something that we're going to later on talk about, and that is side channel attacks. So what we discussed so far about security of these systems is that these systems are secure if the internal of the systems are not leaked, okay? But side channels have shown that during the process of, let's say, for example, computing this S boxes or moving things around in rows and columns, if, for example, the computation is somehow key dependent, for example, if this S box is based on the cache, address of the cache, or this row is based on power consumption and all, people have shown that, this value dependent hardware activities could leak partial bits of the key. And they actually managed to leak the keys and then find the keys. Note that this has nothing to do with security of the AES in algorithm level. This is an implementation problem that basically activities are secret dependent. As a result, someone can figure that out. And we're going to have a full lecture on side channels, and we're going to talk about this. So just keep that in mind. The crypto system, the main motivation of side channels is breaking these crypto systems, because essentially there are activities that are dependent on the key. All right, so that's it for today. We're gonna have a computer assignment on this, which is going to be released hopefully by Friday. And next week, I think we don't have a class on Monday, but we will have a class on Wednesday. I'm gonna start talking about sensor security and fault injections. And then I don't think we're gonna have time to start physical side channels. We're probably gonna be a week after that we're gonna talk about physical side channels. So keep an eye out on the computer assignments, and also there will be a form for presentations. So keep an eye on that as well. All right, thanks for staying a little bit longer, and sorry about that because of the class last week. Any final questions?
Where will the computer assignments be released?
Will be released. I'm gonna post it on Campus Wire. It will be on Gradescope. But I'm gonna post the announcement on Campus Wire. You're gonna also see it on the website. Like the project description will be on the website.
Cool. Awesome. Thank you.
Yep.
Hello, Professor.
Hey.
So what about the PTE to join this course? Because I'm not now currently in the wait list.
Yeah, wait, we cleared the wait list, so you cannot be on the wait list.
Okay, so how can I join this
Just
course?
email me today or tomorrow, and I'm gonna issue a PT.
Okay, thank you.
Yeah. Anyone else who wants to get in, just email me and I'll issue a PT. All right, thank you guys. See you later.